Hello, everybody. Thank you for joining us today. My name is Will Bellamy. I'm part of the continuing education team at the COEH at Berkeley. Before we start, I just wanted to share some of our upcoming webinars. So we've got a lot of exciting upcoming webinars in the next few months. On April 15th, Jin Young Kim and Duwon Han will be presenting a dual webinar on their research into human AI interaction in both automated vehicles and pharmacology. This one is in collaboration with the University of Michigan Center for Occupational Health and Safety and Engineering. Again, that's on Wednesday, April 15th. On April 22nd, in line with what our annual conference was on earlier this year, Aaron Maruso from Silent Spring Institute will present on research and community engagement to reduce exposure to PFAS or forever chemicals to improve clinical care. Please come to this one if you've missed the annual conference or if you'd like to dive into even more environmental health work on PFAS. And that's going to be on Wednesday, April 22nd at 12 p.m. Pacific in collaboration with Silent Spring Institute. Then on May 12th, Hannah Frame will present her research on the role of motivation in occupational health and safety. And that's in collaboration with the University of Cincinnati Education and Research Center. And that's on Tuesday, May 12th, 12 p.m. Pacific. For more, you can always visit coeh.berkeley.edu/webinars. I'll put this link into the chat. Wonderful. And now for today's webinar, on behalf of education and research centers throughout the country, we are pleased to present the Industrial Hygiene webinar series. This collaborative effort on behalf of each ERC's continuing education program aspires to provide access to current research supported through NIOSH ERC programs. Thanks for being here today and showing your support for the ERCs. I'm excited to introduce our speaker for today's webinar on aviation fuel chemistry and the implications for occupational exposure to aircraft engine emissions. Just a few housekeeping items. You're going to be muted during this presentation. If you'd like to enter a question, please enter it into the Q&A box at the bottom of your Zoom screen. We'll reserve some time at the end of the webinar for questions. We also have the chat open, so feel free to use it and participate to join the conversation. This presentation is also being recorded and will be made available on our YouTube page within 5 business days. And for continuing education credit, all participants who logged in with their registration email for the full live presentation today will receive an email with a link to an evaluation form that will also provide them with a certificate of completion worth 1 continuing education contact hour. Once that evaluation is completed, you'll be able to access and print that certificate for your records. Now, I am pleased to introduce our speaker today, Onyinye Ezeifeka. Onyinye Ezeifeka is a PhD candidate in environmental and industrial hygiene at the University of Cincinnati under the mentorship of Professor Yevgen Nazarenko, where her research focuses on air quality assessment and occupational exposure to emissions from aviation turbine engines. Her work examines how the transition to sustainable aviation fuels may influence emission profiles and potential health risks for aviation workers. She conducts lab-based combustion experiments to characterize particle emissions and organic pollutants generated during aviation fuel combustion. Onyinye's broader research interests include environmental pollutant control, exposure assessment, and indoor air quality management. Great to have you, Onyinye. I'll pass it over to you and I'll stop sharing my screen.
Thank you, William. Let me go ahead and share my screen. Does it look good now?
That looks great.
Oh, okay. Thank you. Yeah, good afternoon, everyone, and thank you for being here. My name is Onyinye Ezeifeka, and I am a doctoral candidate in industrial hygiene at the University of Cincinnati, Ohio. For the research I conduct at the University of Cincinnati, the central question my research tries to answer is simple, and that is when we change what we burn in aircraft engines, what changes in what workers breathe? So with that, I will introduce the title of today's talk, Changing Aviation Fuel Chemistry, Implications for Occupational Exposure to Aircraft Engine Emissions. So before we proceed, let me give you like a quick scenario to hold on to throughout this talk. 5:30 a.m. in the morning, a fueler walks up to an aircraft on the ramp, and then he connects the hose. Then the engine of the aircraft is running like, say, 8 feet away, and the exhaust or ground idle is almost invisible. So this means there is no visible smoke and nothing dramatic is happening. And yet the air around the plane or the aircraft is full of particles too small for our naked eye to see. The particles are there, and so is the mixture of the chemical compounds that comes from the aircraft exhaust. The exposure to workers is also happening at the same time. Over a 30-year career, and of course, some of these aviation workers do put in 30 years on the ramp. How much has that worker actually breathed in? So that's a question for you to answer or take a guess on. But my answer would be nobody truly knows. We do not have the longitudinal exposure data or sufficient epidemiological studies, as well as biomonitoring data to ascertain this. And we are now changing the fuel that the aircraft burns, which means the exposure profile may be shifting without us even knowing. That gap is part of what our research group at the University of Cincinnati is trying to close. So as a way of introduction, aviation is responsible for approximately 3% of global greenhouse gas emission. To some of us, this number is not so big, but it represents an enormous quantity of fuel that is being burned, and almost all of that fuel is being burned right now using petroleum-based fuel called Jet A. The chart on the right side of this slide shows a projection from Statista in 2019, and the message here is clear and simple. Emissions from aviation are expected to roughly double by 2050 as air travel demand continues to grow, especially in North America, Asia Pacific, and the China markets. The aviation industry, on the other hand, has committed to a net zero carbon emission by 2050. That is an incredibly ambitious goal for an industry that is very hard to electrify. But then you may want to ask, so how do they want to do this? Their primary strategy for getting there, and that's the one with the broadest industry consensus, which is the use of sustainable aviation fuel. But there is a catch. Changing the fuel changes the combustion chemistry, and changing the combustion chemistry changes what comes out of the engine. The climate benefits here may be real, but the occupational health implications remain largely unknown. So let's start with the fuel itself, because to understand the exposure, you first have to understand what is being burned. First, we have conventional Jet A that I mentioned earlier, which is a complex mixture. We are talking about hundreds of distinct hydrocarbon molecules, all derived from crude oil. And then the key chemical classes are, you can say, N-alkanes, isoalkanes, cycloalkanes, and aromatic hydrocarbons. But I'm going to focus on aromatic hydrocarbons, and the reason is because they make up about 15 to 25% of fuel by volume, and they are the primary precursors to soot formation in combustion. Aromatics is what feed the nucleation and growth of soot particles. They also produce what we call polyaromatic hydrocarbons, PHS, when combustion is incomplete. And many of these PHS are classified as probable or possible human carcinogens by the International Agency on Research on Cancer. And Jet A also contains sulfur compounds. That's about 3,000 parts per million. And you might want to ask why sulfur matters. It matters when it's because it is oxidized during combustion and it produces sulfate particles that contributes to the secondary aerosol burden in the exhaust plume. And all of this is tightly regulated for energy content and thermal stability under the American Society for Testing and Materials D1655, which is a kind of standard that defines the minimum property requirement for Jet A for use as turbine aircraft or aviation fuel, and it also lists all the acceptable additives for civil and military applications. But those specifications say nothing about emission toxicology. So the second type of fuel being burned now is SAF, Sustainable Aviation Fuel, which is currently used as a drop-in fuel, meaning that it can be blended with conventional Jet A and used without the need to modify the aircraft engine. So it can work on existing aircraft engine. And it is made from non-petroleum sustainable feedstocks. And the International Air Transport Association, IATA, they've also identified SAF as the single most viable pathway for the aviation industry to meet its decarbonization targets by 2050. 2050 has a lot. The life cycle carbon analysis for sustainable aviation fuel shown in this image on the right suggests up to 80% reduction in net carbon dioxide emissions compared to conventional jet fuel, that's Jet A. By 2050, sustainable aviation fuel is projected to account for 65% of aviation fuel needs. That's like approximately 449 billion liters annually. That is a massive scale up from where we are today. And this also means that we have an opportunity to formulate and select SAF in such a way that the transition to sustainable aviation fuels will lead to a reduction of exposure to air toxics in aircraft emissions before that 2050. So I'll just talk a little bit about the feedstocks that is being used for SAF production. They are diverse and the source matters, not just for sustainability or certification, but potentially for the emission profile of the end products. Most of the raw materials come from agricultural sector where farmers are mostly agrochemical reliant. They use agrochemicals like pesticides, herbicides, fungicides. And the problem here is that some of the active ingredients in these agrochemicals can also persist into the production chain for sustainable aviation fuel. The major categories are municipal solid waste for the sustainable aviation fuel sources, municipal solid waste, wooden agricultural waste or residues, used cooking oil, and algae. So each of these feedstock has a different chemical fingerprint, which feeds into the conversion process, and which in turn affects the composition of the byproduct. That's the final fuel that is being produced. And the diversity of feedstock and production pathway is part of what makes characterizing sustainable aviation fuel emission very complex. So we are not talking about just one single new fuel. We are talking about an entire family of fuels produced from the different feedstocks and produced through different conversion pathways. The SAF industry has a longer history than many people realize. It goes back to 2007 when Honeywell Universal Oil Product introduced the first renewable jet fuel process that was for military application. And then in 2008, Virgin Atlantic flew the first commercial flight using a blended biofuel from algae-based feedstock. Then the American Society for Testing and Materials approved blending up to 50% for biofuels in 2011. And if you fly down to 2016, you see that the first commercial SAF producer, Hot Air, became operational. Two milestones that I wanted to hold on to here is that in 2021, the first passenger flight using 100% SAF in one engine took place. That means it's actually possible to run aircraft on 100% sustainable aviation fuel. And then in 2022, the US launched the FAST grant program. They recognized the fact that they need to invest in this area. And then a $244.5 million federal investment was introduced specifically to accelerate SAF production capacity by in this industry. So by 2023, 90% of the biofuel market was derived from oilseed and sugarcane, thanks to the US farmers. The point of this timeline is SAF is not a pilot program anymore. SAF is entering commercial aviation at a large scale, and at no point in that timeline did anyone add a milestone for complete occupational health assessment of worker exposure or what workers would be exposed to. As of early 2026, there are currently 11 sustainable aviation fuel production pathway approved by the American Society for Testing and Materials for use in commercial aviation under the standard regulating the technical certification of SAF, which is the ASTM D7566. 3 of the 11 ASTM approved sustainable aviation fuel pathways are co-processing pathways, and they all fall under the D1655 Annex 1. So co-processing basically means it's more like when an existing refinery simultaneously processes 2 or more feedstock, for example, an approved renewable feedstock for SAF along with a petroleum-based feedstock. The 5 pathways shown on these slides are the most widely used. So we have Fischer-Tropsch SPK, synthesized paraffinic kerosene. This is basically produced through gas synthesis using iron or cobalt as catalyst, and it can be blended up to 50%. And then we have the hydroprocessed ethers and fatty acids synthesized paraffinic kerosene, and it's formed by the hydrogenation and deoxygenation of fatty acid ethers and free fatty acids. And it can also be blended up to 50%. Then there is synthesized isoparaffins, SIP, which has a lower blending limit of 15%. And this is because they contain almost no aromatic, and this is very necessary for aircraft fuel system performance and certification. We also have the one in Annex 4, which is the same as Annex 1, but with aromatics. That's Fischer-Tropsch hydroprocessed SPK. And then we also have alcohol to jet, which is also approved to be blended with Jet A at 50%. The production pathway matters because it determines the aromatic content, the hydrogen content, as well as the sulfur content of the final fuel. And what these pathways all have in common is that most of them produce a fuel that is highly paraffinic and very low in aromatic content. That low aromatic content is central to the environmental claim. I also want us to note that when SAF is blended with Jet A, they are being recertified as ASTM D1655, that is Jet A. Very important. To summarize all I've discussed in this first part, Three numbers tell the story of where we are today with aviation fuel transition. 65%, that is the International Air Transport Association estimate on how much of aviation decarbonization pathway must come from SAF by 2050. 0.3% is how much of global jet fuel was actually SAF in 2024, though that is like 3 times over what was obtained in 2023. So the growth rate is increasing and is increasing at a high speed. And 50%, that is the maximum blend ratio currently allowed under ASTM standard. Full transition to 100% SAF is still a future goal that is pending approval by the relevant parties. But from the timeline slide, you could actually tell that it's possible to run 100% SAF. So what these numbers mean in practical terms is that, and the message that I want to pass here is that we are at the very beginning of a fuel transition that will unfold over the next 25 years. And the occupational health data to inform that transition safely simply does not yet exist. Let's talk about what we currently know about SAF emissions. We do have existing literature that have looked at SAF is blend compared to Jet A. And the existing literature covers non-volatile particulate matter, primarily soot mass and black carbon from SAF blends. We do have work by Dodina et al., Johns-Doty et al., and Lobo et al., and they help us to establish that SAF combustion generally reduces particle number, particle mass, as well as black carbon compared to Jet A. Then we have the work from Kobe et al., and they did a great job at comparing particle size distribution between the fuels and the blends, and also help us understand there are actually differences in particle size when you compare to Jet A. Then Corporan et al., the Air Force Research Laboratory has characterized combustor performance with different fuels. So they look at how the combustor performs using SAF and its blend. And then Mazaeri group looked at heavy metals in airport emissions more broadly, but that is applicable here. But here is what literature likely does not address. Not the VOC's profile, the aldehyde profile, the chemical speciation of the particle phase, and most importantly, what any of this means for workers who keep the airports running. Almost all of the existing work was conducted from an environmental or atmospheric science perspective. So there is that gap. These images show the world we are talking about. SAF is not a future concept. It is already in supply chain. These images were images I took in Frankfurt, Germany 2 years ago when I was visiting my husband. And they show the actual infrastructure, SAF storage tanks at airports, fueling operations underway, and the workers who make that operation run being there. So this brings us to the central mechanism that we care about, why the changing chemistry matters. Fuel composition affects combustion and how completely the fuel burns and under what thermodynamic conditions this happens. That in turn changes how particles form, the size, the number, and chemical makeup of the soot that comes out of the engine. And it also alters the gas phase emission, the VOC, aldehydes, and other chemical species in the exhaust stream. But there is a critical question embedded in this slide, written in red. So does lower emission by mass guarantee lower health risk? The answer is not necessarily. Soot mass and particle number do not kind of move together in a way, in a simple way when you change the fuel. A shift to a fuel that produces fewer but smaller particles could actually present a higher deposited surface area does to the lung, because surface area and not the mass is what drives many of the oxidative responses that underline particle toxicity in humans. So now let's now look at what the engine actually produces, what is in the plume that a ramp walker is breathing. Aircraft engines emit two broad categories of pollutants. We have gaseous emissions and particulate matter. The gaseous fraction includes carbon dioxide, water vapor, nitrogen oxides, carbon monoxide, and a complex mixture of VOCs and other organic pollutants. On the other hand, the particulate fraction is dominated by ultrafine soot particles with smaller contribution from sulfate particles and organic aerosol. What makes this particularly important from a health standpoint is that many of these compounds are not just general air pollutants. They have been classified as hazardous air pollutants or probable carcinogens. The aircraft engine is not simply burning clean hydrocarbons and producing water and carbon dioxide. The combustion process, if you permit me, is complex, it's imperfect, and it's variable. And the exhaust also reflects this complexity when you take a look. So I want to quickly spend a moment to explain why particle size is so important. This is because it directly challenges how most industrial hygienists are trained to think about particle exposure. Aircraft turbine engines produce particles across three size ranges. We have the nucleation mode particles below 10 nanometers, which form by condensation of gas phase species. We also have ultrafine particles that are within the range of 10 to 100 nanometers. And lastly, we have fine particles between 0 nanometers and 2.5 micrometers that account for most of the particle mass. Here's the important issue. Almost all particles from aircraft turbines fall in the ultrafine range. And you may ask why this matters. This matters because ultrafine particles deposit deep in the alveolar region of our lungs. That's the gas exchange zone. And their small size allow them to easily translocate across the epithelium and enter our bloodstream. And once they are in circulation, they can reach our hearts, the brain, and other important organs of our body. And there is enough or a lot of cardiovascular and pulmonary toxicology literature that shows the danger of, being exposed to ultrafine particles over a long period of time. There is the risk of respiratory tract diseases, cardiovascular diseases, and also cancer. The second point on this slide connects back to fuel chemistry. So aromatics in the fuel feed the soot formation pathway, and serves very low aromatic content is expected to reduce particle number, but the evidence is not yet fully established for all combustion conditions, and shifting particle size distributions are currently still being characterized. So aside particles, the exhaust stream also contains several classes of gaseous and organic pollutants with direct industrial hygiene relevance. VOCs, this include heavy alkanes in the C18 to C14 range. We also have naphthalenes and aromatic compounds. Interestingly, VOC concentrations are usually highest at the low engine power, like idle and taxi conditions, which is precisely when ground crew are closest to the aircraft. Some of these VOCs are respiratory irritants, and others are classified as potential carcinogens. Aldehydes, particularly formaldehydes and acetaldehydes, are important to industrial hygienists because OSHA has a ceiling limit for formaldehyde of 0.75 parts per million over an 8-hour time-weighted average. This is already a concern in indoor aviation settings like the hangar. And some data suggests that sustainable aviation fuel combustion may actually increase aldehyde output under certain conditions compared to conventional fuel. And that is a finding that warrants careful attention. PAHs also are formed from incomplete combustion of aromatic compounds. SAF lower aromatic content is expected to reduce PAHA output, and that will be a genuine benefit to us. Finally, we have sulfur compounds, which is we have sulfur compounds, and the near elimination of sulfur compound is expected with SAF due to the differences in the feedstock. Then lower sulfur means less secondary aerosol formation, which is a real benefit for both the environment and also for exposed workers. So far, we've talked about what published literature does measure particles, NOx, CO, carbon dioxide. But I want to pause here and ask a different question. What are we not looking at? The answer is the EPA and the FAA have identified more than a dozen compounds in aircraft engine emissions or exhaust that are classified as hazardous air pollutants under the Clean Air Act. These are not hypothetical contaminants. They have been measured at airports. They are listed because there is sufficient evidence from occupational studies, animal models, modeling, and epidemiological data in other scenarios that they can cause cancer, damage nervous system, or even harm the respiratory tract. And yet, if you go through the Jet A or SAF emission literature, almost none of these compounds appear as primary measurement endpoints. For example, aldehydes, look at the aldehydes, that's formaldehyde, which is an International Agency for Research on Cancer, Group 1, non-carcinogen. And acetaldehyde is also a Group 2A probable carcinogen. Then we have acrolein, which is so reactive that it causes acute upper airway irritation at concentrations as low as 0.1 parts per million. Then there is propanaldehyde, which has been specifically flagged by the International Civil Aviation Organization as a representative hazardous air pollutant from airport sources. Then let's move to the aromatic compounds. We have benzene, which is a known cause of leukemia with an OSHA permissible exposure limit of just 1 part per million. And then there is naphthalene, which is the most abundant PHA measured in airport air samples. There is toluene, xylene, ethylbenzene, styrene. All of them are also listed as hazardous air pollutants, all detected in aircraft exhaust, and they are essentially absent from SAF comparison studies that we currently have. Then there are other ones like the 1,3-butadiene, which is also another Group 1 non-carcinogen, and it's basically produced in incomplete combustion. Then there is N-hexane, which causes peripheral neuropathy with chronic exposure. And then we have the PHS and polycyclic organic matter, POM, which bind to surfaces of ultra fine particles and gets carried deep into the lung as well. And then we have metals like iron, chromium, lead, and nickel that come from both engine wear and fuel combustion. The last point I want to make is that a ramp walker is still exposed to these metals, like whether the aircraft is burning Jet A or established. So it's present in both kind of fuel. When people talk about SAF as a solution to aviation's pollution problem, the the implied promise is that workers will be better protected. And for some pollutants, that may be true, but for the entire category of hazardous air pollutant, and especially for the metals and the combustion-derived compounds, we simply do not know. The data does not quite exist. So who is actually at risk and how do they come in contact with these pollutants? So these pictures probably are pictures that we've seen. We've probably seen people at the airport doing one or two of these activities. These are mostly the people that are exposed to these emissions. So let me be more specific about the groups here. We have the ramp agents and fuelers, including baggage handlers, aircraft marshallers, and cabin cleaners. They represent the highest exposure group because they spend their entire shift on the apron and often within a few meters of running engines. There are a couple of other aircraft with different types of engines there, and then other vehicles as well. The um the exposure is not a brief event. It is continuous background accumulation that accumulates over a career. Then we also have the ground support vehicle operators, like the pushback truck drivers, the de-icing truck operators, the ones that clear out our eyes during winter. Then we have belt loader operators. And these ones, they face a compound exposure problem. Why do I say this? They are breathing both the jet exhaust and the diesel exhaust from their own vehicles simultaneously. So the problem here is disentangling the two sources is more like an analytical challenge that a few studies are currently trying to figure out. Then we have the MROs, that's the maintenance, repair, and overhaul technicians. And these ones face a different exposure scenario in that they have less continuous but higher peak concentrations during specific tasks like engine run-up testing and ground runs. Then they also work in an enclosed hangar environment, which means exhaust concentration can build up rather than disperse. Then we have airport firefighters. They are a particularly understudied group, and the training runs using aviation fuel are a regular part of their work. So it is important to also note that emissions dispersed from engines of all aircraft during the different operating modes of the aircraft, idle, taxi, landing, or takeoff. So workers are exposed to emissions of multiple aircrafts at the airport, not just the one that they are next to. Now, I do have a question for you. Which of these worker groups would you prioritize for exposure assessment? You can share your thoughts in the chat box. So, let's quickly look at the primary exposure pathway. That's how workers are exposed to the emissions. Inhalation is the primary exposure pathway, and it is the one that we care most about from a pulmonary and systemic health standpoint. The dose a worker receives depends on three factors: the distance from the engine operating condition, and the time spent in the plume. Distance matters here because particle concentration drop off rapidly with distance. Though the rate depends on wind, the layout of the airport or turbulence or other environmental factors. And we also have engine conditions, and this matters because emissions are highly variable across the power cycle, whether it's idle or takeoff or whatever. Idle produces higher VOC emissions, while takeoff produces higher particle number emissions. And time spent in the plume is, of course, dose determining. The three highest risk scenarios for ground workers are marshalling aircraft, where the worker is positioned directly in front of the engine, intake, and exhaust, and then fueling near running engines and also maintenance engine runs in hangars. These are the tasks we need to prioritize for exposure characterization and engineering controls. And this answered the question from the previous slides. So the Larsen et al. Study from Copenhagen Airport in 2014 is one of the few papers with real personal monitoring data for this workforce. And in their study, they found that baggage handlers had significantly higher ultrafine particle exposure compared to the other groups studied. They also interestingly included security personnel as one of those that were also one of the workers that was also exposed to significantly higher ultrafine particle emissions. So the secondary pathway is the one that is most often overlooked in airport exposure assessment, and is dermal contact. Workers can actually come in contact with aviation fuel and exhaust-derived compounds through fuel handling, through contaminated personal protective equipment that has previously absorbed particles and vapors, and through settled particulate matter on work surfaces. And these are relates to workers like the cabin cleaners. Then PHS in particular are lipophilic and can absorb through the skin with meaningful efficiency. And a worker who handles aviation fuel daily and does not use skin protection has a dermal exposure pathway that is added to their inhalation burden. So most occupational exposure assessment at airports focus almost entirely on air monitoring, why dermal exposure is kind of, rarely measured. This is a gap that our research group will not directly address in its current phase, but it is important to name it explicitly as part of the full exposure picture. So this brings us to the state of knowledge and its limit. The chemical composition of particulate matter and VOC pollutant from self-combustion remain largely uncharacterized. You may have heard me say this a couple of times. And particularly at the operating conditions most relevant to ground operations. Many of the exhaust compounds we know are present, PHS, transition metals, ultrafine particles. They are toxic and also carcinogenic at levels documented in other occupational settings. So we need the one for this particular group, right? And whether they reach those levels in aviation ground operation for self-burning aircraft, it's kind of genuinely unknown at this point. And the fundamental occupational question, whether SAF is safer, equally safer, or potentially worse than Jet A in some exposure scenario, it has not been answered. So let's quickly look at our experimental approach at UC. The centerpiece of our experimental setup is a custom designed high pressure lab scale aviation fuel combustor. Both views of the combustor are shown on this slide, and the combustor is designed to simulate the thermodynamic conditions of an aircraft gas turbine engine in a controlled laboratory settings. This particular combustor operates at elevated pressure, and it uses heated compressed air at set temperature, and then the fuel is delivered through a pressure swell atomizer within an air swirler nozzle, which kind of produces a swirl stabilized flame. And this swirl stabilized flame is kind of the same combustion geometry that is used in real aircraft combustors. The sampling probe, this has a sampling probe, and then the sampling probe is what helps us to extract exhaust from the combustor exits. And the exhaust is then diluted to bring particle concentration into the working range of our instruments. Before I proceed, I know some of you may be thinking, why not just study real aircraft at the real airports? Well, it is a fair question, and there are a few studies of aircraft emissions, but they have quite a number of limitations. A controlled laboratory combustor lets us isolate fuel chemistry as the variable. When you're in the airport, you are looking at multiple engine types, multiple fuel batches or fuel types being run in the aircraft, varying ambient conditions, seasonal variations, wind dilution, vehicle traffic, and a dozen other confounders. In the lab, we can hold everything constant except the fuel. That lets us attribute differences in emissions directly to the fuel chemistry. Also, lab scale studies helps to reduce costs, and it enables frequent and flexible experimentation, and it allows us to test conditions like very high equivalence ratios that would be logistically difficult or safety limiting with a full test, with a full scale engine test. And to look at the bright side, findings from the lab is what we then like directly inform how we design field exposure studies and how we prioritize which scenario, which field, and what conditions to investigate in the airport environment. So that is why we are doing a lab scale study at this point. Our central hypothesis is that emissions derived from self-combustion will yield distinct profiles of toxic and carcinogenic organic pollutants, as well as unique particulate matter characteristics compared to emissions from Jet A under equivalent operating condition. In simple language or plain language, we expect exhaust to look different chemically and physically when you burn SAF and it's blend. The question now is how different, in what direction, and what does this mean for the people who are breathing it? Then our core research question is, how do particle size distribution and organic pollutant profile change when aircraft engine burn different fuel blends, and what do these changes mean for worker exposure? The second part, what does it mean for worker exposure, is what distinguishes this work from what others are doing, or most of the existing SAF emission literature, which stops at just characterizing the emission without making the connection to occupational health. So we are not assuming SAF is better for workers. We are characterizing the differences across the full spectrum of pollutants so that the occupational health implication can be evaluated based on evidence. So let me briefly go through the slide. We test across 4 equivalence ratio, and this helps us to just mimic the actual operating condition. So phi equals 0 is our lean condition. That means excess air relative to fuel, and also means lower combustion intensity. This simulates engine idle condition, and this is the most important condition for ground worker exposure. Then we also have phi equals 1.0, which is stoichiometric. Here we have ideal fuel to air ratio, and the combustion is balanced. This corresponds to like taxi mode. And we also have phi equals 1.3 to 1.6, which is our rich condition. And here we have more fuel relative to air. So this basically simulates like takeoff. And all the runs are conducted as constant air temperature and pressure, depending on what you want to achieve. And yes, we need a full range to give practitioners accurate information about exposure conditions workers actually encounter. This diagram here shows our complete sampling train. Exhaust exits the combustor through a probe inserted into the exhaust duct. It travels through an aluminum tube towards a T-fitting, and dilution air, which is filtered and particle-free, is introduced through a mass flow controller after passing through a HEPA filter and activated carbon solvent capsule. And this helps to remove any background particles and gases to avoid cross-contamination. The diluted exhaust then proceed to the instrument suits. Dilution is important for two reasons here. It reduces particle concentration to the working range of our instruments, and it quenches gas phase reaction and particle phase changes that could artifactually affect our sampling. We are also very careful about the sampling train, the kind of materials we use for the design. We use electrically conductive tubing and keep the line lengths as short as possible to minimize particle losses from electrostatic deposition, diffusion, and wall interaction, which is very important for preserving our particle measurements and for accurate size distribution with our instruments. For sampling approaches, we have a couple of approaches. We can use the solid phase micro extraction tube, SPME, which captures volatile and semi-volatile organic compounds directly from the gas phase. It is a solvent-free method, particularly suited to capturing the VOC and PHA species we are most concerned about. And we also have solid phase extraction tubes, SPE, and it is used for aqueous extracts to capture water-soluble organic species. Then there is the series 110B spot sampler that collects aerosol particles on a substrate for subsequent chemical and morphological analysis, including electron microscopy characterization, we will see on the next slide. And there is DNPH tubes, which specifically targets carbonic compounds like formaldehyde, acetaldehydes, and other aldehydes. And this we are using because given the concern that SAF may increase aldehyde output under some conditions, we feel like this is a critical part of the sampling design, so we can actually capture all the carbon that are present in the emissions. So once samples are collected, they move to two analytical track, chemical characterization and physical characterization. For a part of the physical characterization, we use direct reading instrument, FMPS, fast mobility particle sizer, optical particle sizer, as well as scanning mobility particle sizer to capture, to do the direct reading of all the particle differences, and helps us to look at the particle size distribution and concentration of particles. Then for chemical properties or chemical characterization, HPLC and GCMS is best suited for this, and this is what we be using to see all of the VOCs or organic pollutants that are present in the exhaust emissions. So to talk about expected outcome, we expect this work to produce three categories of outputs. First, comprehensive chemical profile of toxic and carcinogenic organic pollutants for each SAF type and blend ratio that we test. And second, identification of the systematic differences in the abundance of specific exhaust compound. As we already know, these SAFs come from different feedstock. You also want to know which one has more of these compounds depending on the feedstock. So you want to be able to link some of these to the feedstock. And not just saying whether SAF is cleaner in aggregate, but which compound increase, which one decrease, and under which combustion condition those changes are most pronounced. That is what we want to achieve. Then the aldehyde question is a prime example. If if SAF increases formaldehyde at lean condition, that is directly actionable for industrial hygiene practice in aviation maintenance settings. Third, database evidence to inform best practices in field formulating or formulation and blending, giving the industry the information it needs to make SAF adoption decisions that also account for worker health and not just carbon emissions. And let me add the fourth one. The emission indices we generate at each equivalence condition will serve as a source term for a future, like say, breathing zone exposure model, like linking what we measure in the combustor to estimated exposure for real workers at real distances from real aircraft. The broader impact of this research is in two folds. First, we want to advance occupational health and safety, specifically in aviation industry, and to use the SAF transition as an opportunity to do that, not just to reduce carbon emissions, but to reduce the health and environmental burden of aviation on the workers who make it function and who makes all the activities go on smoothly. And we want to give the industry data it needs to identify, blend, and formulate SAFs with the lowest emission of toxic and carcinogenic compounds. And then policy and practice will follow the data. So right now, the data is insufficient, and this research is more like a step in the right direction towards closing that gap. So let me close with two take-home messages. And the things I hope you carry with you. First is that the shift to sustainable aviation fuel is happening now. It will change what aircraft engine emit. Industrial hygienists needs to be at the table for this transition to happen, and not just waiting for maybe field studies to come along in a decade, but shaping the research agenda and the occupational monitoring framework now, while the transition is still new and early enough to influence. And second, aviation workers, particularly ramp agents and the maintenance, repair, and overhaul technicians, they face real poorly characterized exposure to ultrafine particles and complex chemical mixtures coming out from what the aircraft engine emits. And existing occupational exposure limits were not designed to capture the exposure burden these workers carry. And our current monitoring tools are not that sufficient. And this workforce, they deserve the same attention and rigorous occupational health attention we bring to other industry with demonstrated chemical exposure risk. So I'd like to conclude here, and thank you very much for your patience and for listening to me. I'll be happy to take your questions. I am also a work in progress, so I'll appreciate your feedback, your comments, and your advice. Thank you.
Thank you so much, Onyinye, for this presentation on sustainable air fuel. I think this idea of balancing environmental benefits with occupational health is really important. And it was really interesting to hear about your research. We do not have that much time for questions. I think we'll just do one question right now, and I put Onyinye's email in the chat for anybody that would like to follow up. But just time for one question. Somebody asked about how engine maintenance is influencing how workers are interacting with SAF. Um, I was curious if you've found that when we've started to use these blends of Jet A and SAF, has that changed how engine maintenance has worked? And do you think that could influence also worker exposure?
That's a very good question. We haven't fully addressed that yet, but it's an important direction for future work that we can look at. So maybe.
Great. Thank you so much, Onyinye. Unfortunately, we're at time, but feel free to follow up with questions with Onyinye's email. I'm just going to drop it in the chat once again. Thank you for coming today and hope to see you at the next one. Thank you so much, Onyinye.
Thank you. Thank you, everyone.
Bye, everybody. Have a good day.